Hello and welcome to the Preparatory workshop for the Part 3 Foundations courses. This will be the last video in Computability. This is relevant for the Model Theory and Non-Classical Logics course, and because just a part of the course will be on Computability, this will be a short video, and it's meant to sort of provide a picture of some sort of important theorems here, rather than actually give formal definitions. So this quest in Computability was started with a question of Hilbert and Ackermann, which was to find an effective procedure or an algorithm to determine if a given sentence in a first-order language is a tautology, meaning whether it can be proved from the axioms and no hypothesis. So this was referred to by Hilbert as the Entscheidungsproblem, and famously, just 8 years after it was sort of proposed, Church and Turing independently, they showed that there is no such algorithm. Okay, the first question that might sort of come to mind here is that how does one show that there is no algorithm to do something? Well, for this to be a precise mathematical statement, first of all, it must be that there's a precise mathematical definition for an algorithm. And in fact, several different formal definitions were given out, and they all turned out to be equivalent. So, what is an algorithm? Informally, an algorithm is a finite sequence of instructions which, essentially given a finite input, they either perform some computation or they solve a problem. Now, okay, this could be any finite input whatsoever, but in fact, we want to look at inputs which are natural numbers. Okay, why is that? Well, in principle, any finite input could somehow be encoded by a natural number, and this, in principle, can be achieved in a way that can be reversed effectively. So, kind of the important information about a problem can be effectively understood and reversed, the encoding, just from the natural number that is supposed to represent this input. Okay, formally, what were the different approaches to capturing mathematically this notion? So Gödel first, in 1933, proposed a definition of general recursive functions. So Gödel's functions were a class of partial functions from powers of the naturals to naturals, which were produced by a certain fixed set of rules, starting from elementary functions. So these are functions on top tuples of naturals. They give back a natural, and they sort of perform some kind of computation on the tuple, and they give an output. Okay, but these were sort of developed very abstractly. So just from basic kind of steps, and from these basic steps, from these basic functions, we expand onto more complex ones by using the rules. I won't explain these rules now, but that's basically the idea. And this set of general recursive functions of Gödel, they in fact include most standard arithmetic functions. Okay, like addition, multiplication, exponentiation, polynomials, whatever. Yeah, almost everything that you would expect that you can compute. So later on, in 1935, Church proposed what is known as the lambda calculus. So this was a totally different approach. The lambda calculus is a formal system which is based on function abstraction and application using variable binding and substitution. Okay, so think of logic that essentially manipulates certain terms in a very kind of similar fashion. This lambda calculus manipulates these terms, which are supposed to represent computable functions. And these terms are of the form lambda x dot y. Okay, and x is supposed to be the input, y is supposed to be the output. So the terms of this formal system are supposed to be the functions under consideration. And within this system, Church defined an encoding of the natural numbers, and though this allowed to define lambda computable functions on the naturals, as those whose church numerals the functions, the corresponding functions in the church numerals were lambda, were definable in this system. Just a year later, in 1936, Turing gave a totally different definition and it took a different approach to this, which I guess is the one that is probably the most intuitive. So Turing proposed what are known as, and defined what are known as Turing machines. So a Turing machine is a very theoretical and abstract model of a machine, consisting essentially of a finite set of states and an infinitely long tape, which the machine manipulates. And what it does is that it is able to read on it and write, read from it and write on it. The choice of what to read depends on the tape's header. So there's a header that points to a certain element in the tape. And the choice of what to write depends on the current state on which the machine is in. And after each such step, the machine essentially transitions to a different state and it moves the header, it either stays or it moves to the left and the right. And so it processes somehow this tape. And the input is initially presented in the tape. The output is the content of the tape after having reached a special end state. And this allows to define Turing computable functions, again on the naturals. We can think of the sort of alphabet that the content of this tape is in. We can think of this as the naturals. So we can define computable functions, the naturals, as those whose, when you place their input, as those such that there exists a machine with the property that if you place their inputs on the tape, the outcome of the machine after reaching its end state is the output of the function. Okay, so I'm giving this definition very informally and hand-wavily. It can be very formally stated, but that's not really the point here. What I slightly hinted at before is that all of these notions, all of these very formal notions, were in fact shown to be equivalent. So as I said, for all of these, we can define what it means for a function on the naturals to be computed by each one of the three sort of systems. And it turns out that these that functions on the naturals are generally recursive if and only if they're lambda computable, if and only if they're Turing computable. And this was shown by Church, Kleine, and Turing. And this motivated what is known as the Church-Turing thesis. What this says, and the reason why it's a thesis and not a theorem, is because, well, it's not a formal mathematical statement. But what it says is that these equivalent notions of computation, which a posteriori came up in order to capture an intuitive kind of understanding of what it means for something to be computable. The thesis says that all of these equivalent notions precisely in 100% captures what can by any means be calculated by any effective method. Okay, so it's more of philosophical statement, but it's one that is highly motivated by the fact that all of these systems and all of these approaches that were taken and that have been taken so far to define what it means for something to be computable have ended up being equivalent with regards to the functions and the naturals that they can compute. Okay, as a consequence to this property and to this equivalence between these notions of computability is the fact that there are functions in the naturals which cannot be effectively calculated. So this in fact comes from an easy counting argument. Why is that? Well, the set of functions from naturals to naturals is uncountable. So there are uncountably many such functions. On the other hand, there are only countably many Turing machines. Therefore, uncountably many functions are not Turing computable. Okay? So this is a very non-constructive argument showing that there are in fact functions which cannot by any means be effectively calculated. A very important concept here is that any Turing machine, being a finite object itself, it may be given as input to any other machine after encoding. And in fact, this was crucial in Turing's proof of the undecidability of the Entscheidungs problem. The crucial bit is that this encoding is effective, and so once we've encoded a machine, there's a way to decode it, and in fact there's a way for the machine to simulate it and to run it. So given a machine M, we write hash M for the code. Okay, and what Turing showed, amongst other things, is that there's a universal Turing machine. That is, there's a Turing machine U, which given the code of a machine M and an input X, it simulates M on X and returns the output of this computation. Okay, so this, yeah. Right. Now, given a Turing machine and an input, we say that the machine halts on this input if at some point eventually it reaches this designated end state, infinitely many steps. Otherwise, we say that the machine loops on this input. And the possibility of looping on an input X is precisely what would make the corresponding sort of computable function from the perspective, or the general recursive function from the perspective of Gödel. It's what it would make this partial, and it's why Gödel considers partial functions. The halting problem now, which was defined by Turing in the paper where he showed the undecidability of the Entscheidungs problem, is the following. So the problem asks if there's a Turing machine H, which on input the code of a machine M and an input X returns yes if the machine M halts on X, and otherwise returns no. In other words, is there a way such that given a machine and an input, we can tell algorithmically if the machine will halt at some point in this input? And the answer to this, as shown by Turing, is no. And I'll sketch a quick and sort of informal idea of why this is the case. So assume for a contradiction that there is such a machine, H. Consider now the machine, which on input, the code of a machine M, it will run H on the tuple, the code of M, and the code of M, and returns yes if H rejects and otherwise loops. Okay? So this defines sort of an algorithmic process. In fact, it formally defines a Turing machine, but since I haven't given you a formal definition, I couldn't show you why. it gives rise to a formal machine. But nonetheless, intuitively, this is sort of a well-specified sequence of procedures, so this defines a machine. And then what we do is that this machine A, we run it on its code. Then observe the following. If the machine A halts, then it must be that it does so because H rejects the input, the code of A, comma, the code of A. But for H to reject its input, it must be, recall that H decides if something holds or not on an input, it must be that A doesn't hold on its own code. But we started with the assumption that A holds on its own code, so that's a contradiction. Assume, on the other hand, that A doesn't hold on its own code, that it must be by definition that H accepts the code, that H accepts the code of A, comma, the code of A as input. And therefore, that's by definition of what A does, and therefore, by definition of what H does, it must be that A holds on its own code, but that's also a contradiction. Therefore, we cannot determine if A holds or doesn't hold. Either one of the two cases gives a contradiction. It follows that no such A can exist, and consequently, no such machine H can exist. Okay. Therefore, the answer to the halting problem is negative. We cannot tell if, given a code of a machine and an input, that machine will halt on the specified input. And from this, we may reduce the negative answer to the Entscheidungs problem. Why is that? Recall that what we want to do here is that we want to decide if a formula is a tautology. But in fact, we can sort of encode we can represent the halting problem in this context. Why is that? Well, in an appropriately chosen finite language, which I won't specify here, we can construct for each Turing machine M and for each input X a formula phi in this language, such that phi is a tautology if and only if M holds on input X. Intuitively, what this formula says somehow in this carefully chosen finite language is that there's a sequence of configurations of the machine on input this X that starts at the initial configuration, the initial state. It stops at configuration which is in an end state, right? And the existence of such a sequence of configurations implies that M holds on X, okay? And in fact, it precisely captures that. So phi is a tautology if and only if M holds on input X. It follows, therefore, that if there was a positive answer to the unsigned problem, so if we could tell computably if something was a tautology, we could computably tell if a machine could hold on a certain input. So we would get a positive answer to the holding problem. But, as Turing showed, this cannot be. And therefore, this was how Turing obtained his negative answer.